Now, if we combine the two, now we've made multiplication much cheaper. So here I'm showing you such an example where one of the operands of the multiplication is a pulse train. That's operand A. And in this example, it has half the number of pulses, so it represents half the maximum number. So in this case, it's 0.5 is what I showed you before. And then we have the second operand, which is a race logic operand. And here, because it's a race logic operand, we only have one pulse. And in this case, it's a value of 0.25 because that one pulse drives in time slot 0.25. The key to making this work is we're going to use the race logic operand to suppress any other pulse train operand input. So in other words, every pulse that comes from this first operand, the pulse train operand, will be propagated to the output until the race logic operand arrives. And that will suppress any further other output pulses. And if we do that, the output is the multiplication of these two in a pulse train format. So in this case, it's 0.125. In this other example, where just the values are different, the multiplication output is 0.375. And why did we do all this? Well, because now we can multiply two numbers, a pulse train and a race logic number. In the unipolar case, which is what I showed you, we can do that with only one cell, an NDRO cell. So now we've made multiplication so much cheaper than it used to be. Even in the bipolar case, which I didn't show you, but it's the same logic. We can multiply with 4 cells, 2 NDROs, 1 merger, 1 inverter. And the whole thing and multiplication now just becomes so much cheaper. I promised you to quantify this trade-off, and here it is.